These are the notes for AP Calculus on the topic of logistic growth part 2. So on this one it says we've got a fake news story spreads through social media at a rate where Y is the proportion of the population that has heard the fake news story. So notice it doesn't tell you it's logistic, but you can tell because the variable here is Y and Y appears here and here with a minus sign. That does fit a logistic differential equation. And then notice what's different about this one. Usually the carrying capacity represents the actual population. This time it represents the proportion, which is another way of saying the fraction or percentage of the population. In this case, it's the fraction, though. So when we draw our graph, we're going to still have that horizontal asymptote right at the carrying capacity. And you can see it's 1 because 1 is like, when the proportion is 1, that's like 100%. That's like when everybody has heard it. Now it doesn't tell you the initial value, so we just have some initial value here. And then the graph, again, would have this shape to it. Concave up and then concave down. And where that point of inflection is, it's always at half the carrying capacity. And that's what proportion of the population has heard the fake news story when it is spreading the fastest. So it's spreading the fastest right there when it's the steepest, and that's when it's half the carrying capacity, which is just 1/2. So that's the proportion of the population that has heard the fake news story when it's spreading the fastest, 1/2. All right, now let's take a look at one that would be more of a free response type of a question. It says the size of a population of armadillos living in a nature preserve at time t is modeled by the function y equals AFT. So there's two different things we're calling it, both y and AFT. And notice it does tell you it's the logistic here. It's already in the right form. You can see that y is already isolated here. And so you can tell right away the carrying capacity is 360. And time here is measured in years. But here, notice the initial amount they're telling you is b, where b is a positive constant. Because in the different parts of the problem, they change what that initial population is. In part A, it says if b equals 50, what's the largest rate of increase in the number of armadillos in the nature preserve? So it's asking for something a little bit different here. So let's draw a graph first of our logistic growth problem here. Again, we'll put our carrying capacity in. Which is where we have the horizontal asymptote. In this case, it's 360. And then for part A, we're going to have a different graph for part A than part B. So part A, it starts at 50. And then again, it starts out concave up and then concave down. And where that point of inflection is, where it switches from concave and up to concave down, is again half the carrying capacity, which is 180, half of 360. But here it doesn't ask at what population of armadillos does it increase the fastest. It actually asks for what is the rate itself, which refers to the derivative. So we know it occurs at y equals 180, but to actually find the rate, you would actually have to substitute into the derivative. So here we actually find the actual rate itself, dy dt. When you're substituting something, remember you draw the vertical line. This specifically when you can either put y or a. I'll just put y because that's what in our equation there for the derivative. Y equals 180. So let's substitute that in here, see what we get. So we'd have 1 over 1800 times y, which is 180. And then we've got 360, our carrying capacity, minus y, which again is 180. So let's see if we can simplify this. Well, you can see 180 goes into 1,800 10 times, so that's 10 on the denominator. 360 minus 180 is 180, and 180 divided by 10 is 18. So it's not always going to be an integer, but this one is. So you get 18. That would be the actual slope right here where it's the steepest. And it says indicate units of measure. So the units come from right here. Y is the same as A of t. Remember, represents the population of armadillos. So in this case, 18 would be 18 armadillos. Per, the units for time in this problem are years. So armadillos per year. That's the largest rate. That's answering the question. And then it'd be explain your reasoning. So it'd be since $180, that's what we put in, is 1/2 of the carrying capacity. $360, and our initial population at 50 was less than 180. We'll see why that's necessary when we get to part B, but it's less than half of the carrying capacity where we started, which is why that ends up being the steepest place. So that would be your answer right there for part B, for part A. Then for part B, we've got a different initial population. It's actually 200. So that actually changes the graph a little bit from what we usually see. Oops. As notice, 200 is actually above half of the carrying capacity. So we still have the carrying capacity at 360. That doesn't change there. But the 200 here, our initial amount, since it's above the place where it would usually switch from concave up to concave down, where usually it would be the steepest, we're actually not going to, since it's above 180, we're actually not even going to see this concave up part because it's starting up here. So we're only going to see it's just going to be concave down the whole way because it's more than half the carrying capacity. So it's just going to be like that. So where it's the steepest, because it's concave down, it's actually steepest right at this initial, because it's concave down, the slope keeps reducing as we move to the right here. So it's right at 200. So that's what you would substitute in this time to find the largest rate of increase. So it'd be dy dt this time specifically at 200, when y is 200. Equals, so we've got 1 over 1800 times 200 for y right there. And then our carrying capacity 360 minus 200 for y. So let's try to simplify this one. So here, you can knock off the zeros there, and you can see 2 goes into 18 9 times. And then 360 minus 200 is 160. And 9 is made up of 3 times 3. 3 doesn't go into 160, so in this case that doesn't reduce at all. So as you can see, you don't always get a whole number. We get 160 over 9. That's the slope right there at the steepest point. And again, the units are y over t. Y is armadillos, t is years. So armadillos per year. And in this case, your justification would be since you start off the same way, 180 is 1/2 of the carrying capacity. $360, and this time the initial amount A of 0 equals 200. It's actually greater than half the carrying capacity, so that's where it's the steepest. As opposed to the last one, that's why we had to say the initial amount was less than half the carrying capacity, so that makes it steepest at the half of the carrying capacity like it usually is, but in this case it's actually steepest at the initial amount since it's above that carrying capacity. And then part C says let B equal 60. And using Euler's method, starting at t equals 0, with 2 steps of equal size, so a review from Euler's method, approximate A of 4, the number of armadillos at time 4. So to figure out the step size, which remember we call delta t, you would take, in this case, wherever you're trying to approximate, 4 minus where you're starting at 0, so it'd be 4 minus 0, divided by the number of steps is 2. So in this case, our step size delta t would equal 4 divided by 2 is 2. And then remember the way you use Euler's method, you have a starting point, which in this case, instead of x and y, it's t and y, or you could put a here if you want. And our starting point on this first one is right here. They tell you a of 0 is b, so in this case, on this particular problem, it's 0 for time and 60 for y. And then we have to find the derivative at that point. In this case, notice it only involves y. So that would be 1 over 1800. And then for y, we'll put in the 60 times 360 minus, again, we'll substitute in the specific y of 60. So 6, you can knock off those zeros here. 6 goes into 18 3 times, so 6 goes into 180 30 times, so we're left with 30 there. And then 360 minus 60 is 300, and 300 divided by 30 gives you 10. So 10 represents the change in the y, and then remember you always multiply that by the step size. So, sorry, that's not the change in y, my bad. That's the slope there. And then you multiply that by the step size, which we just figured out over here was 2. gives you 20, and that represents the change in the y, which in this case is 20. And then you add the old y coordinate, or the initial y coordinate was 60 here, and that gives you your new y coordinate of 80. So that's one step, one time through the Euler's method process. And then we go back here. Now the t increases by the step size, which is 2. And then 80 is our new y coordinate. So now we need to figure out the derivative there. So it's again 1 over 1800 times this time 80 goes in for y. And then 360 minus 80. And then when we reduce that, we knock off the zeros here. 8 doesn't go into 180, but 4 goes into both of those. So 4 goes into 8 twice, and 4 goes into 125 times, and to 80 20 times. 25 and 20 gives you 45, so we have 2 45ths there. And then 360 minus 80 is 280. And then you can divide 45 and 280 both by 5. That gives you 9. And then 10 would go into 280 28 times. So 5 goes in twice as many times, 56 times. And 9 doesn't reduce with the 2 or the 56. So you go to 2 times 56 is 112 over 9 times the step size of 2. 2 doesn't reduce into the 9 either. So this time our change in y is 224 over 9 plus the old y coordinate was 80, which if you multiply by 9 is 720 over 9. Which, add those together, gives you 944 ninths. And so that's our second step, and now we're done because that's what tells you is at 944 over 9. And we're asked to approximate A of 4. The only thing else we have to do, notice it says round your answer. Since we're talking about armadillos here, you can't have a fraction of an armadillo here. So round your answer to the nearest whole number. So you could say A of 4 is approximately, 9 goes into this, well, 9 goes into 900 100 times, and there's 44 left over. 9 goes into 44 4 times. That goes into 100. 4 times, and that's 36. So there's 8 left over. 104 and 8 ninths. So that would round to 105 armadillos. All right, and then the last part, part DS, determine whether approximation part C is an overestimate or an underestimate for the number of armadillos at time 4, when b equals 60. So let's draw a graph of it. You could have done it in part C, but we really didn't need it there with Euler's method. But here, to visualize it, to see, makes it a little easier if we draw the graph. So again, our carrying capacity is 360 still. Oops. the initial amount, this time is 60, the initial population. And since that's below half of the carrying capacity, we'd start out concave up and then concave down. And again, it would be steepest right there at 180, and 60 is below that. So on this one, it's similar to the local linear approximation. You can see this whole thing is concave up, and Euler's method is really just a bunch of linear approximations. So if you just sketch this on here, oops, you can see when it's linear, when it's concave up like this, the Euler's method here is just using a bunch of these linear ones here. In this case, we use two different steps. You can see it's less than the actual value of it. So we're underestimating, or it's an underestimate in this case. So we can say 105 armadillos is an underestimate of A of 4 since, explain the reasoning here. Well, it's since A, our graph here, is concave up on this interval, 60 to 180. And notice even our approximation of 105, that's still below 180, right? So this whole part is concave up. If it exceeded this, if our approximation was above 180, then we would know for sure, because then part of it would be concave up, part of it would be concave down. So in this case, because our initial value and approximation are both in this interval, we can see it's concave up, and that means it's underestimated. Versus if our initial and approximation were between 180 and 360, then we would see it's concave down, then it would be an overestimate if it was there. If it does on both, then they wouldn't ask you, because then you wouldn't be able to tell for sure if it's both concave up and concave down on the interval. And that concludes the notes for AP Calculus on the topic of logistic growth, I should say, part 2.